this first plenary session of the day. My name is Peter Conway, and with Deb down here, we're chairing this first plenary. I'm going to take 2 or 3 minutes just to introduce you to Antarctic Science Limited. The reason for that being that this first plenary is known as the David Walton Memorial Lecture, and that is a reflection of a long-standing relationship between SCAR and Antarctic Science. Now, I'm going to flag a couple of things that hopefully are of interest, particularly to early career scientists, but also to everybody in the room. Antarctic Science Limited is a charity based in the UK that runs the journal Antarctic Science. By virtue of being a charity, what that means is that anything profits, dare I say, that are made from the journal are ploughed back into Antarctic Science bursaries, and that is a scheme that is specifically aimed at early career scientists. I'm not going to read all the lines on the slide, they are there for you, but this is an opportunity for early career scientists to apply for some form of project, travel support, training support that enhances what they are already doing. I'm sure there are several recipients of this over the years in the room.
Including our guest speaker here. Right. For those of you who like QR codes, that's a way of finding it. Obviously, the bursaries also have a website and a contact email. The journal itself, of which I'm currently chief editor, is a very broad, cross-disciplinary Antarctic science journal. Very much like these SCAR meetings, we have a scope that covers anything that takes place within Antarctic science. The only submission limit is that whatever you're submitting has to have something to do with Antarctica, and that can include comparisons with the Arctic, gradients out of the Antarctic, all the way to the tropics and so on. We explicitly encourage submissions from all countries, institutions, individuals undertaking Antarctic research. We're a pretty standard journal. We publish original research papers, reviews, perspectives, opinions, and so on. Something that may be of interest to session conveners here, but is always there as an invitation. We're very keen to receive proposals for special issues, and they can be quite narrow in scope, a particular session at a meeting like this, for instance, or very broad in scope. Anybody who's interested in that, just get in touch with me, or again, get in touch with the journal email. So coming on to today, Professor David Walton was a terrestrial ecologist at the British Antarctic Survey for many years. He effectively was responsible for setting up the journal and setting up the charity, and also the initiation of the link with SCAR. He died a number of years ago, and this lecture series had already been set in motion at that point. So it's since then that we've renamed this the David Walton Memorial Lecture. This year's lecturer is Mathieu Casado, behind me here, who is a paleoclimatologist based in CLRS in Paris. Has a particular focus in his research on ice core records and the use of water-stable isotopes to help interpret those in a climate context. He too is very closely involved with the APEX community, particularly in the context of linking them with IPCC processes. He's an editor for the Journal of Glaciology, and not surprisingly, given he's lecturing here today, he's been to the Antarctic a number of times and is very experienced in his field. I look forward to your lecture, and welcome.
Thank you. Thank you so much. Okay, it works. Brilliant. Thank you so much. I'm very honored to be chosen for this David Walton Antarctic Science Lecture. And I would like to also thank all the organizers of the SCAR conference, as well as all of you for coming very early this morning. I I hope you all enjoy the half-free Wednesday for some of you. And when I received this invitation to talk about climate change in Antarctica, I was a little bit worried because, as I will try to convey today, climate change in Antarctica is a very delicate topic, in particular because of the constant attack of climate skeptics trying to find loopholes in every science about Antarctica. And so, after advice from a couple of wise colleagues here, I decided to not go necessarily for a very exhaustive review of like everything that there is, and the topic was too large anyway, and to do more like maybe an opinion lecture. And so I will also take a few opportunities to make like a couple of points that are dear to me about climate change and about Antarctica. And so I will start with the fact that there are more and more like early warning signs of the current climate crisis in Antarctica. And one example is this heat wave that just happened last month, where average temperature 10 degrees above normal were observed. And I will make this an opportunity to make my first parenthesis. And it's personal opinion about being a climate scientist, working in Antarctica and living in the context of climate change. We all have to actively reduce our greenhouse gas emission because this is the only way to, viable way to mitigate the effects of climate change. And flying, and including flying to a conference like this one, is of course a major contributor to greenhouse gas emission. And yet, when I noticed like the absence of, like, or the very few number of French scientists to this conference, I was discussing with them, and I'm a bit conflicted by the response that they all like decided to stay and access it to this conference remotely, or like not all of them, we're a couple of few people here, because to reduce the greenhouse gas emission. Because I feel like Europe as a historical greenhouse gas emitter should also have this duty to not necessarily isolate itself and refuse to travel to conferences that are outside of Europe, because by doing so, they're de facto forcing other countries, like people in South America, for example, to travel to Europe, and basically they're exporting carbon footprint onto those countries. So this is my first rant, and it's over for now. I will go back to the topic at mine with another like of those early warning signs that I found, and this was this mind-boggling extreme event with this atmospheric river with almost 40 degrees anomalies that happened in Antarctica. And there was this recently published paper from Jonathan Willey and colleagues showing the extent all around East Antarctica where this was more than the 95% percentile. And this led to the Conger ice shelf breaking. So this extreme event have extreme impact also on Antarctica and the ice shelves. So the IPCC reports have been very clear about the imminent crisis. And for Antarctica, there still remain a lot of uncertainty, and this is what I want to talk to you today. And in particular, if you look at this technical report from 2021, it's written specifically over all land regions with sufficient data, i.e. all except Antarctica, observed change in temperature have clearly emerged outside of the range of natural variability. So there is a clear lack of data in Antarctica. This is something that's been said by the IPCC and also by SUS, and a lot of members of SUS are here today, lamenting the lack of data in Antarctica and in the Southern Ocean. And I will try to show you how this is a very clear gap. I stole this slide from Nerily because she did the lecture, the David Walton lecture 4 years ago. And the slide was brilliant, so I just took it as it was. And it really shows, here in red, you can see the observed trends for the last 36 years when they were preparing this manuscript. They even extended it to 41 years, showing that there is no clear signal of the warming in those observations, despite climate models, for example, here in black, showing that force simulation predicts a warming, with this working title that they have about 41 years isn't enough because the data were too short. Other proof could come from this Nicholas and Bromwich paper from 2014. And here they had a little bit more than 50 years. And yet, they were able to identify a clear trend in West Antarctica, in the Antarctic Peninsula, but in East Antarctica, it was still missing a lot of data points. And overall, the trend for all of Antarctica was limited to below 0.1 degree per decade, which is less than the global average. And so this was a little bit puzzling to me, because on the other hand, you could see such articles as the one from Kyle Clem, who is here, and his colleagues, showing that for like stations like South Pole and Vostok, you could have significant warming, up to 0.6 degree per decade, which for context is as large as what we observe in the Arctic and 3 times the global average. And so how can we reconcile anecdotal evidence like these 2 stations with huge trends and the lack of trends shown by reanalysis products and ensemble of weather stations? So this is a little bit what I want to talk to you about today. One first suggestion came already in the literature from this paper from Jones et al. In 2019, and I'm going to try to break it up to you a little bit. So here you can see the trends from all the weather stations. The first point to notice, in Antarctica, they only had 23 weather stations that they could use. This is very little for an area of more than 10 million square kilometers, more or less the size of Europe. And overall, what they could see is that in West Antarctica, they had a significant trend, which they show with those like circles around the dot. But in East Antarctica, the trends were not significant. And they tried to see if one of the causes for that could not be the impact of SAM. So SAM is the southern annular mode, and for those of you who are not familiar with it, it's very, very roughly the intensity of the wind around Antarctica, which tend to isolate and prevent storms traveling towards Antarctica. And storms carry moisture and carry heat, so they can be responsible for heating up the continent. And here what they show, all of those points are quite blue, meaning that basically the SAM congruent trend is leading to a cooling, an effective cooling for all of these stations. And they were trying to evaluate what could be the background warming, the background warming trend hidden under the influence of SAM. And here they find quite significant warming with trends that could be larger than 0.2 degrees per decade. And at this point, being an ice core scientist, it's not that I don't trust weather stations, but I was like, can we see something with ice cores? And could ice core provide a historical context? I'm already convinced that ice cores are awesome, and so my goal today is to convince you that ice cores are maybe even better than weather stations in this context, mainly because we have more. A quick break again, I'm using mostly water isotopes to study past climates, and so why do we use water isotopes in ice core? I'm just going to do a quick break from that. You don't necessarily need to understand all of it from my presentation, but just to explain to you. And there have been found a direct link between isotopic composition of ice and snow and temperature. And this was done by Willy Danchka and Claude Loyus in the 50s and the 60s. They traveled across Antarctica during, you can't really see this pointer, but they traveled across Antarctica, taking samples of snow, measuring the temperature, and what they found was this linear empirical relationship between isotopic composition and temperature, basically making an isotopic paleo-thermometer. And again, it's a little bit more complicated than that, because the idea is the signal is acquired across the hydrological cycle. Over the ocean, you would have evaporation, which induce fractionation. Fractionation meaning that heavy isotopes will remain preferentially in the condensed phase, so here in the ocean, and this leads to vapor phase and clouds that are depleted compared to the composition of the ocean. We use this delta notation, so a depleted value means the delta value is negative. Then, as most air masses are affected toward polar regions, there is cooling, so then you have precipitation. And again, heavy isotopes are going to preferentially stay in the condensed phase, so first in the rain, then in the snow. And this happens until you reach your ice core location in Antarctica, where you could have very little amount of snow, and it's piling up, and you get stratified records. because all of these steps are temperature dependent, at the end you obtain isotopic records, that is archiving the temperature across the hydrological cycle. Again, it's a bit complicated because we're integrating a lot of processes, so it's still quite a noisy record, but it's a very precious record. And there was this Pages2K compilation. A lot of people among you are part of this initiative to try to get all the isotope records that could be used to reconstruct past climate, not only in Antarctica, but in the world. And I'm using the one from Stenny et al. 2017. They had more than 50 records, some of them covering more than 200 years. They were able to identify 7 coherent regions. Here I'm going to highlight those 3 regions in particular because I already showed them to you. West Antarctica, again, what they found is similar than weather station, is a clear positive trend that you can see here with the gray bar, that outside of the range of natural variability. But for East Antarctica, using ice cores and with trends over 100 years, they were not able to find such a trend again. So basically, ice core were agreeing so far with weather station. And so to kind of summarize the situation where my team and I, when we started to look at this topic, where there was this attested warming in West Antarctica and in the peninsula, the anecdotal evidence in East Antarctica, but there are only very few weather stations for a huge territory, and ice cores are not necessarily detecting something different than weather station, even though we have more in East Antarctica, but they're also very noisy. And so the question is, like, maybe having more ice core, we can reduce some of this noise. And when we started this study, what we wanted to know is, we need more ice cores, but how many, where, and once we have them, when should we be able to detect any signature of the anthropogenic climate change in Antarctica? So this was our mindset. A little bit of a spoiler, we actually realized we already had enough ice cores. And so why were we able to find this, why our colleagues found something different? We need to go back to how we calculate a trend. It's, I know, very basic probably for most of you, but the idea is, here I just did a simple mine experiments where I have a time series with no trend for the first 50 years, and then a trend of 0.1 per mil per decade for the next 50 years. Per mil per decade is this isotopic unit, but it's not necessarily important. You can imagine it's just 0.2 degree per decade. It's more or less a factor of 2 between the two of those. In a real context, you need to include also some natural climate variability. Time series in climate are not so smooth. So then it's a little bit more difficult to actually visually see this trend, but we have numerical estimators that we can use that will simplify this for all of us. In this case, one of the key factors when you need to calculate a trend is you have to choose a window, and this is where it gets difficult because we don't want to have something that's subjective. If you take a short window like here in blue of only 30 years, you get a large uncertainty. This is a Monte Carlo simulation with 10,000 peaks. You still get the right average. And if you take a window that's a little bit too long, like here 100 years, only half of your window has a trend, so you're virtually diluting the trend, and then your average value is not right. And like I wanted to see in this context, with a 100-year slope, would the Stenny et al. Study be in this, like maybe a bit too long of a trend? So again, we try to pick a 10,000 simulation. This is just one example. And what you can see if you like increasing the window length, for like short window length, you have this noise dominated situation. Then you have some sort of a plateau that's converging towards the right value of the trend. But as soon as your window length is longer than the duration of the offset of the trend, then you have this dilution. And if you try to plot the data from Stenny et al. On top of this, you see actually exactly the same behavior with this noise dominated for short window lengths, then some sort of a plateau converging around 0.12, and there's this dilution. And what they picked was 100 years, and like I would argue here that this probably was a little bit too long to actually evaluate the right trend. But again, like there is a little bit of an issue with cherry picking and saying, I'm gonna just pick the right trends because this fits what my agenda. And So, of course, like we want to pick the best estimate, but at all time, one should avoid having to do this cherry picking. I discussed with like some statisticians in my institute to like how can we move a little bit beyond this framework. And I'm not going to necessarily explain to you the entire dynamical system framework because it will take more than this lecture. But here we used one of those indicators, which is called the persistence, which is basically the average time it needs to go back to the average state. And you can calculate this for every single data point. There is no choice of any windows. What you can see here, when you add a trend, it's going to take more and more time to go back to the average state. So you see an immediate rise of the persistence where the trend is starting. Natural variability will try to counteract this because it's a little bit widening the average state. So overall, if you're able to evaluate your natural variability independently, for example, we can do spectrum before the trend kicked on, we get an estimate of trends using the persistence, which doesn't have any preconceived choice of what should be the window length. And so we applied this on all the available ice cores from the ISO2K networks. There were 78 ice cores across Antarctica, which is a little bit more than 23 weather stations. We used a spectral calibration for isotopes. I'm not going to go into detail about this, but basically we have a factor 2 between isotopic composition and temperature. And this matched what people were observing at Dome C, for example, in precipitation. We did a lot of more spectral analysis to try to evaluate should we be able to see a trend. And a trend here for climate change is basically a decadal signal. So here, using spectra, we could see that we have a signal-to-noise ratio that's relatively positive at decadal scale with correlation of 0.75 with the common climatic signal. So again, we were like very puzzled that those trends were not detected. And so what we see here is in the context of the last 1,000 years, in the center you have the delta Etino anomaly, and you can see this time series with, of course, a lot of natural variability. But in the last 50 years, you can see this clear increase that match relatively well the orange of the weather station. So we're really providing an extended context for weather station in Antarctica. And when we use the persistence where we don't have to fix the window length, we can clearly see that for the last 50 years, the persistence value are largely above what was natural variability with 2 standard deviation for the last 1,000 years. So to try to summarize in a bit of a simpler figure, here the square is basically the trend for the last 50 years, and we obtain a trend of 0.22 degrees per decade, which is larger than the ensemble of the distribution of trends with this bar, and also larger than the global warming, so indicating a polar amplification. I'm not going to have a lot of time to go into polar amplification details, but it's a very important factor that explains the fact that you have larger variability and potentially larger warming in polar region. And it's something that's very attested for the Arctic, but was not necessarily clear and clearly defined in Antarctica. If we compare to ERA 5 finds a similar warming, but again, like people were a bit cautious because the time series are very short. And CMIP models, here I'm using the past 1,000 simulation, show that there is also a warming that's larger than natural variability, but not as high as what we observe in the observations here. And so this was one of the aspects also that worried us, is that there could be an underestimation of the amplitude of climate change by climate models. And I will get back to this. If we look at individual regions, so here in blue I'm showing East Antarctica, in yellow the Antarctic Peninsula, and in orange West Antarctica, we see similar results where ice cores overall indicate a larger warming than what was found for the natural variability, and also larger than what models have been finding. I'm also going to link this a little bit with the Arctic. My colleagues from the Alfred Wegener Institute led this paper with quite a few ice cores from Greenland when they found very similar results last year as well. And this is extremely worrying because they were also able to not only reconstructs the temperature and really shows this warming that you can see here on the top left in black, but also shows that this warming was associated with increased meltwater runoff, so increased melt from Greenland. And they were able to do statistical analysis to show how probable it was. And clearly this indicates that in black red you can see the last 10 years are clearly out of the range of what natural variability could predict. So we are really in a situation where warming and melt have been amplified. So a little bit of few perspectives, because for example, we don't have such results for Antarctica yet, but a few perspectives and a few points that I think like should be really important aspects to study in the next 10, 15 years, and also with the imminent arrival of the IPY, I feel like this could be the point that if I had all the choice for the funding, I would put the money, at least in physical science. So there was a presentation from Edward Hanna this week, and I'm not necessarily going to go into the detail of this paper because this is an instant paper and a lot of you know this probably way better than me. But we already have evaluations of sea level contributions of East Antarctica and West Antarctica. And we can see that Antarctica is contributing to sea level rise overall. So far, West Antarctica, not so much. But we also know from ice core records and from paleoclimate records that Antarctica have the ability to lead to the largest contribution of sea level rise. For example, there were suggestions that during the last interglacial, there could have been a few meters of contribution from Antarctica to sea level rise. And one of the key aspects that I think for me is still going to be extremely important is how can we refine the uncertainties from climate models and also ice sheet models to evaluate what should be the contribution to sea level rise from the ice sheets, both in West Antarctica and East Antarctica. And there are a lot of debate and very healthy and good debate within the community to know which type of processes, for example, for ice shelf calving should be included. One thing that I also want to argue is the climate model, like CMIP and PMIP models, also need a little bit of refinement. One of the things we found is that there is a huge range of warming trends predicted by the different climate models. Here we tried every single CMIP6 historical model, and we see that some of them actually don't even suggest that there is any warming trend in Antarctica. So we have a range of a factor of 3 between the warmest and the coldest warming in Antarctica from those climate models. And considering the uncertainties and the impact of warming in Antarctica, refining this should also help a lot improve the estimation of what should be the warming in Antarctica. And the IPCC has been really clear that this is a key impact of what should happen, for example, for low-lying countries and islands which are extremely vulnerable to sea level rise. And we already see extremely concrete consequences, and there was this manuscript last year suggesting an unavoidable future increase in West Antarctic ice shelf melting over the 21st century. So this is something clearly happening already right now, and we need a lot more data. One thing also we couldn't touch at all, and I'm really keen with this paper from Quentin Daladen, is detection and attribution of climate change. We had such a strong disagreement between our ice core reconstruction and climate models that we didn't feel like doing any detection attribution was necessary. But in this study, by basically adding or not the forcing from climate change, from greenhouse gases and from the ozone depletion, they were able to, for CSM and the other model CAN, they were able to evaluate what should be the contribution of those different contributions. And this is absolutely key to be able to better understand the polar amplification, and especially in Antarctica, with all the consequences that it can have for sea level rise and as well for the environment in Antarctica. And finally, and again, because I already said that multiple times, we need more data. So there are about 27 weather stations now covering more than 50 years in Antarctica. In Paris region, we have 63, and weather forecast still sucks. We're not able to predict the climate next week. So if we want to predict how Antarctica is going to behave in 100 years, we need absolutely more stations. So taking action, I think at the scale of SCAR, I would really feel like a call for more in-situ observation is necessary, following, for example, the statement of Seuss last year. Could be installing new weather stations, and I think IPY is a perfect platform for that. Could also be making me happy and making more ice cores across Antarctica, because I still feel like ice core records have a lot of things to say for this community. I'm also going to take a couple of minutes to speak directly to early career researchers. So some of you might recognize this logo of APEX. I've been participating in APEX in some capacity. I'm still in the advisory committee. I'm going to speak a lot about my personal experience within APEX, but this is true for every single early career network. So if you have another favorite early career network, please use this. And within APEX, in the last 7 years, we've been able to link with the IPCC, and they welcomed us. We created a group. We were a few people, not so many, 5, 6 at the beginning, relatively well organized, and had the support of APEX. And we were able to work with IPCC authors, with the technical support unit, with the IPCC co-chairs. They welcomed us because we had APEX stamp and because we were generally interested into proposing solutions and helping the science. And they need our help. I'm now not so much of an early career scientist. And we have so much burden, we can't have any imagination. So we need early career scientists to also think of imaginative solutions. And with this type of framework, we were able to publish several papers and realize the review of the last 4 IPCC reports. And this has been listened and welcome. So if you have any type of idea, even the most ambitious one, do not hesitate. You can speak with APEX, you can speak probably with your mentors, and I'm sure they will support you and guide you, introduce you to the best person. One of the person, for example, for me, who was instrumental in this was Renuka, who really helped me and pushed me at the last in-person meeting for SCAR in Davos to try to really move forward with this project, and this was extremely helpful. So if you have questions, you can come to me, but come to every mentor and every person here, and I'm sure they will be delighted and provide amazing advice. And so to kind of summarize, we started this with the question, when and with how many more ice cores will we be able to detect the signature of climate change in Antarctica? And what we found is at the scale of Antarctica, we already do. And so now, if we want to have more focus and to be able to go at local scale and regional scale, and there are a lot of very interesting questions to do that, not necessarily only looking at the scale of the continent, we'll need more ice cores and more weather stations. I know I'm insisting quite a lot of this, but I truly think this is extremely important. And I'm very enthusiastic about the incoming IPY. I hope that we can all participate, and I'm very glad that there was a meeting yesterday and there are more opportunities to discuss on how to lead an effective activity and move forward on those topics. So thank you so much, and if you have any questions, you can ask me or these very cute penguins.
Thank you, Matthew, for the wonderful talk. We've got time for some questions, so quickly raise your hands. I can see Tom here.
That was really interesting. Thanks very much. And yeah, in the context of detection, I was wondering what the potential is for using spatial information for detecting fingerprints of change. Because using the station observations, Gillett et al. In 2008, we managed to detect a human fingerprint in the spatial patterns of change over Antarctica. So, yeah, I was just interested in whether that might be possible for paleo or ice core records.
Yeah, so I was trying to hear a bit better. Yeah, I think we have quite a few spatial concerns. like 27 stations in Antarctica, 2 of them are inland. So obviously, this is also going to lead to a clear bias towards coastal region. And we all know, for example, in Europe, coastal regions are behaving differently than interior regions. We have different degrees of freedom if we're looking at viability in marine areas versus in continental areas. Here, since we're speaking about kind of a relatively homogeneous warming across the planet, I feel like the number of degrees of freedom are relatively low, so the spatial viability should be a second order parameter. I think the first PCA, if you want, would be like really like this node that's basically a bit warmer across Antarctica. Sorry about that. I don't know if this answers the question.
Hi, I've got a quick question. Really great talk. I just had a question whether historical records from field observations are of any value, because those exist at least back 60 years until the early 60s and late 50s with IGY. Would those observations basically of November through January be of any assistance for this work, or just too noisy?
Yeah, it's a great question. I feel like the seasonality is clearly something that would be a complicated aspect if you only had data from December to January. I mean, actually, there are a few more weather stations that have been installed than those 27. It's just like time series are a bit too short. And something I forgot to mention, that installing a new weather station now, or even like 10 years ago, is not necessarily sufficient, because we're talking about decadal trends. So you really need to have more than 10 years, more than 15 years. Like even, again, going back to what Neredi was saying 4 years ago, like when 41 years was not enough. The more weather station you have, the more like you could have shorter time series, but we're not at that point yet. I don't know if this answers the question.
Yes.
Thank you, Matthew, for that, being the brand ambassador for this ice coat community. One very interesting thing, what's coming up of late, is that there have been a lot of huge, if you look at the accumulation, or even within the isotope data, we find a strong signal of extreme events constituting for the entire, say, a couple of few events constituting more than 40 to 50% of the annual accumulation, as well as the variability. So how do we, as a community, we convince the what you call the observational as well as the climate scientists that our ice core records are actually an annual or a seasonal, averaged, kind of data over decades and, centennial times?
Yeah, thank you so much for that question. That's actually what I spent most of my time working on. And the idea is a single ice core would potentially have a lot of gap and not be able to reconstruct every single year. But once you start averaging several ice cores, because this precipitation intermittency is the fact that it didn't snow in one location, but so you would have a gap, is actually has a shorter decorrelation length than the temperature fields. If you combine several ice cores that are like far enough that the precipitation was decorrelated, you can basically get rid of the fact that you have this precipitation intermittency noise that's added. And so this has been something that has been studied quite a bit. And typically, you're able to retrieve more and more signal for a given time scale. And it's relatively well scaling with the number of, the square root of the number of ice cores. So with 100 ice core, you're able to remove 10% of the noise. And typically, this is what you would need to start to get a good signal-to-noise ratio. So having 100 to 200 ice cores would be like really the dream. So it's not something impossible to attain. That was also one of the important facts that when we were looking at this, is we could really get really good annual to seasonal signal with a relatively modest number of ice cores compared to the work it represents.
So we can have 2 more questions. Yeah.
Thank you very much. Excellent talk. So you've sold me as a biologist that we need more ice cores and more weather stations. What you haven't told me is where you want them. Do you have a plan on where would be the best places to put them? Because we tend to just put them where we work, and what we need is pressure to put them where we need them, I guess.
Yes. Trying to get a map again. I had the same map with the ice core records, and I just forgot to include it in my slides. But typically, we would need, like, where it's the most valuable is where we have the most gaps. So it's also not the most convenient places to go, but maybe for some of you who have more of an adventurer type, like it's maybe the most exciting places to go. So presumably, having a strong network, and this cannot be by a single nation. I think like we need to work together to have a strong network and be able to reach various places. Actually, I have the map from Steny et al. Where you can see a little bit better. So it's quite far away. Here, you can see a little bit better that we have quite a few gaps. For example, in Adeliland, there is a few gaps. In the north, where you see like there are too many data points, this is the Germans who made like 1,000 ice cores just nearby Conan Station. So here, we don't necessarily need many more. But presumably, having a couple of new ones will still be valuable because a lot of them were done in the early 2000s, so they don't necessarily extend to 2024.
So we have the last question from here. Yeah.
Thank you for the very nice presentation. I had a question. How would you, or is it possible to integrate the satellite data record into your research? And wouldn't it be more efficient to invest in satellites instead of getting local observations with weather stations?
Yes. I mean, satellite observations are extremely valuable, and like, there may be the hidden participant here that's not really well acknowledged. Like, we use a lot of satellite data. Reanalysis use satellite data, for example, they're integrated. The issue is, if you want to have long enough time series, we basically need to wait. And I'm not a patient person, like the people here who know me would know that. So in the meantime, I still feel like it would be valuable. There are also still quite a few biases with satellite data, and in-situ observations are still very needed. In terms of temperature, the satellite data are getting better and better. But for example, there is a lot of perturbation with the clouds. But for example, in terms of spectral albedo, so how much is the snow reflecting, there is still a lot of need for in-situ observations. So satellite data are extremely useful. We need them, and like, I'm not gonna also going against deploying more satellite and having better measurements of the conditions of Earth from that. But I also feel like still in-situ observation going to the field has a little bit of value again, yet still.
Thanks. So we can accommodate one quick question. Yes.
Thank you, Matthew. So you mentioned about increasing the spatial coverage of ice cores, but what do you think about in the sites that we already have ice cores, as we have many that were drilled in the 2000s? What about sort of covering the gap between, let's say, 2000 and 2025? So then we would have 25 more years of comparison with the high resolution data sets. Is that valuable in your perspective?
Yeah, sure. I think it's extremely valuable. And since we're always going to go back to the station we're based on, we can, as an opportunity, just drill a quick ice core on the side for 25 years. Is not so many meters, especially inside of Antarctica. So it's quite valuable. There's also value to duplicating archives. But again, like, funding is also limited. So I feel like we have to pick a little bit our battles. So, I mean, the more we can do, the better. I think we still have quite a lot of value to show. Like, studying Antarctica is not something that we've done it and we know what's happening. There's still a lot of uncertainty and a lot of stakes for what's going to happen in the future of the planet. So I think it's still worth investing.
Okay. So thank you. And thank you, Matthew, for the wonderful talk. And Thank you all for being a wonderful audience. Just remember that we are back here at 9:30 for the mini symposium. So take a break and come back. Thank you.
mini symposium for day 4. So welcome to our mini symposium session titled, as you can see here, The Melting Frontier and Its Global Implications, exploring the Antarctic ice ocean atmosphere boundaries and critical interfaces that drive global climate change. A bit long, but my name is Won-san Lee from Corpri. I'm really pleased to convene the session today. As you all know here, the Antarctic ice sheet, its grounding oceans, and the atmosphere above form a complex and dynamic system that plays a crucial role in shaping our planet's climate. As the Antarctic continues to experience rapid changes, understanding the interactions and feedbacks at these critical boundaries becomes increasingly important. Today we have a fantastic lineup of speakers who will be giving and sharing their research and insights on various aspects of this melting frontier. First, we have Dr. Kenny Matsuoka from MPI, who will be presenting on analysis of the current gaps in our understanding of the Antarctic ice sheet margin and help guide us to future research efforts. Next, we have Dr. Laura Horais-Burguero from CISARO, who will be discussing the importance of observing ice shelf ocean interactions and provide advice on implementing effective monitoring programs, international. And we have Dr. Claire S. from Corpri, will then take us to the interface of Antarctic boundary processes, focusing on the crucial role of sea ice and its complex interactions with the ocean and atmosphere. Finally, we have Dr. Emilia Jean from Corpri, explore the ice-ocean interface, atmosphere interactions and teleconnections that are accelerating Antarctic melting and the far-reaching consequences for the global climate patterns. Following the presentations, we'll have a panel discussion and Q&A session where you will have really interesting opportunities to engage with our speakers and explore these topics further. I want to thank you for everyone here and our distinguished speakers for sharing their expertise, and I extend my gratitude to you all being here today. Now let's dive into the fascinating exploration of melting frontier and its global implications. Please join me in welcoming our first speaker, Kenny, who will be presenting his talk titled, perhaps, if I'm wrong, just correct me, Results of Rings Group Analysis, What is Missing Knowledge in the Antarctic Ice Sheet Margin. Please.
Thank you, Won-san, for a nice introduction and for the invitation to this workshop. And good morning, everyone. And thank you for having me here. Thank you. All right. I would like to talk about missing knowledge in the Antarctic ice sheet margin in the context of the Rings initiative today. I have opportunity to talk about rings earlier in this symposium, so maybe you know about rings well already, but just in case, I would like to summarize it very briefly. Rings surveys would go all around Antarctica at 3 locations. The most important one, we call primary ring, will go at the current grounding line so that we can know the flux gate to estimate ice discharge to the ocean. And another important ring is called landward ring. That is some kilometers to tens of kilometers inland of the current grounding line so that we can constrain better topography for ice dynamics. And that location can be the future flux gate location or grounding line. Another important ring is seaward ring over ice shelves and ice rises. The seabed under the ice shelf remains largely unknown, and gravity measurement there is critically important to understand how our ocean will eat the ice in the coming centuries. RINGS is SCAR Common Up joint effort to fill the data gaps in Antarctic ice sheet margin and eventually improve estimate of the current and the future sea level change. So RINGS group has worked to establish scientific rationale as advanced as possible using published result. Now it's a big group effort of about 100 people with about 24 nations. When we casually say RINGS, we may say 3 different things, so I just want to clarify that. One is a SCAR Action Group Antarctic RINGS, that's do the science work and facilitating international collaboration and endorsing individual research and survey project. Common Up has RINGS as well, that is called the Common Up RINGS Collaboration Project to provide logistics knowledge to efficiently survey plans. And the actual survey would be done by RINGS endorsed project. That's the third one, we said RINGS. And then actually these projects really meet the goal while upholding the shared values and the principal guidelines. So many people asked me how we can get this document, so I put a QR code that is openly accessible, and we're very happy to hear any feedback about this. Okay, I'm going to present some results, but it's not something I have made by myself alone, obviously, and it's really a large group effort with these fantastic people. This is a picture taken in the first RINGS workshop back in 2 years ago, and that is really the starting point to realize there are many data gaps, not only better topography data gaps all around Antarctica. Let me start with the big picture, mass balance of the Antarctic ice sheet. And this is not a RINGS result, this is a result from INBI initiative. And then you can see that the Antarctic ice sheet mass balance over the last several decades. East Antarctica, West Antarctica, and the peninsula show different trend and different features, but overall it is very clear that Antarctica is losing the mass as well as Greenland. When we measure current ongoing mass balance, there are 3 methods, and 2 of them is shown here, geodetic method, left one showing the archimetry, satellite archimetry result, and the right one showing the gravimetry method. These methods are very powerful, but we can tell only net mass balance. Another method to understand mass balance is called input-output method or budget method. The mass input to Antarctica is basically snowfall or surface mass balance. And the major mass output term is ice flow discharge. So we measure or model or whatever we do, we calculate these 2 terms and see the difference, that is mass balance. So there are 3 ways to calculate ice sheet mass balance, and that all 3 are very important. Input-output method can possibly tell you why net mass balance is changing. Mass loss can happen with increased ice discharge or decreased snowfall. We want to know why it's happening. The diagram here is also from INBI paper. You can see that archimetry and gravimetry results are reasonably close to each other, but input-output method gave relatively away from these 2. But it doesn't mean that input-output is wrong, but there are such discrepancies, and we are wondering why there are so big discrepancies. Let me start with ice discharge estimate discrepancies. The left showing the Alex Gardner's estimate for the year 2015. You can see the number that is ice discharge in gigaton per year, and the color shows the magnitude. The right one showing the difference between the 2 estimates, Eric Ligneau's and Gardner, for the year 2015. In some regions, you can see the great agreement, but in many regions, their estimates are quite different, sometimes close to 100% or even more than 100%. Niels made a similar estimate, but more recently. So the left figure showing the difference between Miles and Gardner for the year 2015, and the right shows the difference between Miles and Ligneau for the over 18 years of record from 1999 to 2017. For all plot, the darker color means larger difference between the 2 estimates. Let's put the details on side, but the point I would like to emphasize is that when we see these 2, and the right one here, you can see darker regions in quite different locations. So not only the total ice discharge from Antarctica, but regional patterns are completely different between these estimates, and that is we really need to work. Let's look at the mass input side, surface mass balance. Well, when we do the mass balance calculation, modeled surface mass balance is used, and Ross Motran led a very nice community effort to compile 5 different climate model results to see the ensemble result. And the left one is ensemble mean of the 5 models for the last 4 decades. You can see, of course, the desert in the inland of Antarctica, and along the coast, there are very high variability in short distance scales. But more important thing is a central panel. That showed ensemble standard deviation. Darker blue show the area where 5 models give completely different result, exceeding the 100% of the mean. However, observation in Antarctica is quite limited, as the right panel shows. So this is another reason why input-output method is so inaccurate at this moment. But why the modelers cannot model the surface mass balance accurately in the coastal regions? I'm not a modeler, so probably I'm not the best person to explain that, but I really enjoy the view. Now you're all familiar with this beautiful volcano. I took this picture on Saturday or Sunday. Yes, it was beautiful. But then some days, I think it was Monday or Tuesday, it's get cloud all over the top. Of course, I'm not saying that there are volcanoes or such high mountains in the coastal regions of Antarctica. It's not true. But there are many ice rises of several hundred meters above the ice shelf surface, and that makes very strong orographic effect. And that's why the probably modeling there is so difficult. This shows the ensemble mean surface mass balance along the grounding line. Dark blue is ensemble mean, and light blue is ensemble standard deviation. You can see huge difference, spatial difference, and the difference between the models. This is another segment in Antarctica, and going back from Weddell Peninsula to Weddell. You can see all cases, the models do not agree. So we need to improve it. Probably the data, observational data, is very useful to validate them. And I would like to say, airborne radar would be an excellent tool to do it. This is the example of NASA Operation Ice Bridge data over the Martin Peninsula in West Antarctica. And with the regular processing that OIB provide, we couldn't see that. But with special processing by Giroux at the University of Kansas, we can see clear structures near the surface. And if we get ice core somewhere there, we can date these radar reflectors for the age, and we can calculate the surface mass balance in the past. Matthew gave an excellent talk this morning, and he showed a lot of ice cores in the drilling Moderland sections, and that's the race of the German drilling thousands of ice cores there. And actually, Belgian and Indian and Norwegian joined that race as well, and we drilled a lot of ice cores in that region, and we found that all ice cores tell a different story. So here you see the 6 panels from 6 different ice rises along the drilling Moderland. I'm showing the surface mass balance over the several decades in the past. So you can see that the red one showing the time series, blue one showing the time series of surface mass balance derived from the ice core drilled at the summit of the ice rise. And the red one showing the surface mass balance constrained by the combination of ice core and radar together. So it's more regional surface mass balance value. You can see both magnitude and historical pattern are completely different between ice core and radar. So that means that when we validate surface mass balance model result, ice core is probably not the best way. We need radar data together. I would say this is a huge knowledge gap or data gap along the ice sheet margin. This knowledge is also limited in the inland as well, but in the marginal regions, the surface mass balance vary more, and that makes more uncertainties. I already showed this slide earlier this week, so I do not want to repeat it too much. But obviously, bed topography is a huge data gap along the ice sheet margin. But how much measurement do we need? How dense data is necessary to satisfy modelers, for example? We did some exercise about it as a rings group, and this is the result of the Calvin Shackleton made. At the left top, you can see the many black lines in the panel. That's actually showing the location of the radar profile. And the color shows interpretation uncertainty caused by this radar data. The original data is collected at 2.5 kilometer spacing with a great effort of British Antarctic Survey and Alfred Wegener Institute. But we used this data to make artificially low density data. So the panel second from the left showing the 5 kilometer spacing. The next one is 7.5 kilometer spacing. The most right one is showing the data, the 10 kilometer spacing. Although we have more data, but we use only these data to calculate data interpretation uncertainty. And we found that these 10 kilometer spacing can give the uncertainty more than 150 meters very easily. And this is exercise at a location where we expect very smooth bed. So in many locations, uncertainty would be much, much larger. This is just an exercise at one location, so it cannot be generalized so much. But the key message here is that we really need dense radar data to get adequate bed topography data all around the Antarctic ice sheet. That is the exercise about the grounded ice sheet. But when we go to the bathymetry, seabed topography, the situation is even worse. I'm showing the result compiled by the Ibuxo version 2. That is a great global work, a part of the global work. And you can see a lot of ship locations. And also you can see the ice shelves in different colors. And these colors showing the data availability. For example, Ross Ice Shelf has very dense, less than 10 kilometer spacing, airborne gravity data with ground truth, so that is good news. Some ice shelf has only sparse gravity data. And for example, some other ice shelves has no gravity data at all. So we are just guessing about the topography, smoothly interpolating between the deep ocean and the grounded line location. So obviously, seabed is another huge data gap. I'd like to say a little bit about how this poor bed topography can impact the modeling of the ice sheet in the past and the future. And this is a very difficult question. I would like to work more with the modelers to address this question more appropriately, but this is our exercise using the published result and then mainly led by Jenny Arthur of Norwegian Polar Institute. There are a lot of model ensembles from ISMIP 6, but we selected 50, and we plotted the probability of the grounding right retreat in the left map, panel A. The darker blue show that most models agree that ice sheet retreat to that position, and the lighter blue show that more extreme case. You can clearly see that Antarctic grounding line will retreat in the coming 1 century. This is a result, a snapshot at 2100. Let's look at the panel F. You can see the blue there. So yes, model predict the grounding line retreat of 10 or 20 kilometers. And you can also see a lot of black lines there. That is the location of the radar data or bed topography data used for this modeling. Currently, we have more data in that region, but when the ISMIP 6 modeling is done, only this radar data is used because that is all we had at that time. You can clearly see that grounding line retreat is predicted at the location where we do not know the bed topography. So you know what I want to say. The panel H, low, that is a little bit better than the previous region. We have some radar profiles. We know the bed topography in the region where we expect the bed grounding line will retreat, but obviously it is not enough. We need much more data. So again, bed topography, both grounded ice and seabed is real knowledge gap and data gap. How do we measure that? It's a challenge. Actually, Antarctic grounding line is 62,000 kilometers long, and the Earth's circumference is only 40,000 kilometers long. So you see that this is a very challenge. But however, for us, distance itself is not really a big challenge, so we can just keep doing. However, complicated topography of the grounding line is more a challenge. So this is the work done by Guillermo Folt at NPI and Hamish Pritchard at the British Antarctic Survey as a joint effort between RINGS and the BEDMAP 3 to define the grounding line for both the BEDMAP 3 and the RINGS product. They compiled a lot of grounding line data and then determined the contemporary grounding line location. But you can see that it is very hard to do. Different methods detect the grounding line at a different position. Even tide makes the grounding line location different. So it is a very time-consuming job. So it's very nice to have a single product for the both project, and we made it. Okay, let me give some example. Here, you can see the contemporary grounding line, accurate grounding position in red, and you can see the distance scale of the 200 kilometers at the left bottom. It is impossible, practically, to make the radar survey, airborne survey, along this red line. You can see the distance 200 kilometers there. The survey airplane typically fly at 300 kilometers per year, or 5 kilometers per minute. So the pilot turns to left and right almost 10 seconds, and if we do such a things, gravity data is probably not really useful. So it is not really practical to make a measurement along this very complicated geometry of the grounding line. So we decided to make the ring surveys along the simplified grounding line that is shown with blue there. This is a pain decision, but very practical. There's some circles and lines that there showing the how airplane make a turn when we try to hit the position P. To make a position P, we just need to fly and pass the P and come around and make another loop. It is a lot of time and fuel to make it. So I hope I make a very practical sense that we can do this kind of surveys only along the simplified grounding line. But what's the demerit to do it? Of course, we measure the ice thickness very carefully at the simplified grounding line, so we know the flux gate there very clearly. So we can calculate ice discharge there accurately. However, what we want to know is ice discharge from the grounding line, from the red one. So we need to compensate the mass changes between blue and red here. So that means we need to measure the surface mass balance and see the mass changes of this part. So what happens if we do that using the models? That was another question. We actually did that exercise, and the yellow part or orange part in the left figure showing such a promontories or such that we cut off for the simplified grounding line. So the area of them is not so significant. However, these locations has a lot of surface mass balance, a lot of snowfalls, so that the correction, surface mass balance there in total is actually quite large. And the right one showing the more difficult story, that the surface mass balance estimate of these small regions made by 5 different regional climate models give completely different answers. And let's compare these numbers, correction factor, to the regional ice discharge. And you can see that it's not small at all. So again, we started rings with a better topography knowledge gap, data gap, but obviously surface mass balance is also another important data gap we need to fill, and the single airborne radar survey can possibly do in many cases. I would like to show 2 more slides. This matrix showing the rings key science questions we agreed after the workshop. Of course, it's not exclusive, and there are many, many more interesting questions. But these are focus we would like to make, and these are, we believe, most important questions. To hand on to the next speaker, I would like to show this figure at the end. We are going to make more radar surveys, and we enrich better topography information along the ice sheet margin. That means we have a better knowledge where groundwater or subglacial meltwater can flow, and where this fresh water can enter to the ocean. So I hope we have more impact than just for the glaciology. Thank you for your attention.
Thanks a lot, Kenny. Excellent talk, and then also brief introduction to the next presentation. So I'm going to have Laura for, she's presenting, observing ice-ocean interactions. Thank you.
Thank you, Wan-san. Thanks, everyone, for joining us. And thanks, Kenny, for such an interesting talk. I'm going to take you to a different part of the system that surrounds the Southern Ocean. That surrounds Antarctica. So I'm taking you to the Southern Ocean. And I'm hoping to provide a picture of some of the changes that we're seeing in the Antarctic marginal seas in the last 5 years, and how information from ice sheet mass loss and freshwater discharge into the ocean affects the relationship of the ice sheet with the ocean and the climate. I'm sure that a lot of you have seen this video many times. I find it fascinating, and I learn something new every time I look at it. So here we're looking at the GRACE observations of Antarctic ice mass changes from satellite. And you can see that some regions lose ice mass and others seems to grow. But if we reach the end of the time series, we start to see new regions appearing in East Antarctica, and that signal is really dominated for the last 10 years. So that brings me to say that, that I'm gonna take you to an overview of East Antarctica. Oh, there you go. So to understand what drives the Antarctic ice sheet ice mass loss, we need to look to the Southern Ocean. The Southern Ocean has a dominant influence in our global climate as it transports heat, fresh water, and carbon to the deep ocean and around the globe. So changes here will have an impact everywhere else in the globe. And it is here in the Southern Ocean that we see Antarctic bottom water being formed. In the figure, I'm showing you a map of the density of the ocean near the bottom. And the densest waters are in red. And that shows the locations where we see Antarctic bottom water. And the blue lines show you the pathways where Antarctic bottom water leaves the Southern Ocean to the other parts of the globe. And Antarctic bottom water has its origins in the Antarctic marginal seas, where dense shelf water forms. Around Antarctica, we have Antarctic polynyas. And the coastal polynyas are the dominant feature in the winter months. So the figure, I'm showing you the map of, in black is the ocean, in the color you can see sea ice production in meters per year. And you can see that there are certain locations where the sea ice production is really high. And these are the areas where we know dense shelf water forms. And it's only really in 3 major polynya regions in East Antarctica that we see dense shelf water that is dense enough to form Antarctic bottom water. So it is not everywhere around Antarctica that we see this dense shelf water influencing the global ocean circulation. I'm just going to show you a little bit of what kind of observations we see in the coastal polynyas, and that will bring us it will give us a baseline to understand the changes that I'll show later in the presentation. The polynyas are like ice factories. They remove heat from the ocean and they cool the ocean until it reaches its surface freezing temperature, which is when the ocean starts freezing and forms sea ice. And while they freeze and cool, they also rise the salinity of the waters below it. And when they do that, they mix all the way. In some cases, they go all the way to the bottom of the ocean. And that's what I'm showing by these 2 blue lines. So in the figure where I'm showing the temperature and the salinity structure with pressure, I'm showing you the temperature and the salinity in September, which is where we see dense shelf water production more efficiently in the water column. And this is from an arc float. So you can see that we have the same temperature all the way from the ocean surface to over 1,000 meters in this particular coastal polynya. And when you look at the salinity, it shows a pretty similar picture where we see same salinity all the way from the surface to over 1,000 meters. If we look at the temporal changes of where or how this happens, then I show an example in a time series of a moor with several instruments that measure temperature and salinity over time. And you can see that from about April, May, the salinity at the shallower instruments, which in this case appear as the yellowish line, it starts increasing until it matches the salinity at about 1,000 meters. And then the whole water column increases its salinity at the same time. So dense shelf water is the densest water mass in the continental margin. So it will tend to occupy the bottom part of the water column. In this slide, I'm just showing you the link between the ocean heat content and ice sheet mat loss. In the middle figure, you see one of Pritchard's papers published in 2012 where we started seeing mass change around Antarctica and how it related to the temperatures in the continental margins. And if you can see clearly how East Antarctica and West Antarctica differentiate from each other. While in West Antarctica we have really high ice mass loss, we see really warm waters occupying the bottom part of the water column here. So if you look at a section of what the temperature of the ocean is between the deep Southern Ocean towards the Antarctic ice sheet, you see this really warm, deep water mass upwelling and entering the continental margins of West Antarctica, and then making its way to the deep Greenland line where we see really large basal melt rates. But if you go to East Antarctica, you see that it's really cold, and this water that has been formed during the sea ice formation period, and it takes and dominates the bottom part of the water column. And although it's really cold, if it's at the surface it freezes, when it reaches the Greenland line, it's still warm enough to melt the ice, and although a lot lower than what we see in West Antarctica. Yep, so I said that, oops. However, in the last about 5 years, really we have started to see that some places in the East Antarctic continental margins are not as we expected from a coastal polynya system. And in fact, we are seeing regions where they look a lot more like West Antarctica. And I think that was a big surprise for the whole community, quite unexpected. Several examples where we see circumpolar deep water dominating the bottom part of the water column in East Antarctica I've highlighted in the map, and that's the Denman Glacier, the Bundaberg Glacier, and the Totten Glacier. And if you remember the video that I showed at the beginning, this is a part of East Antarctica that is starting to show ice mass loss. And I have the two orange arrows highlight the regions that I'm going to show you next. And these are the ones that we're really just learning not only what they look like, because we hadn't been there previously, but also the state of change that they're going through. I take you back again to the Southern Ocean, and we've seen that in the last, really since the 90s, a really strong warming of the circumpolar deep water layer offshore of East Antarctica. So in this figure, I'm showing you the temperature change between 1950, 1990 to 2010, 2018 at 400 meters deep. And it's 400 meters deep is where we see the really core warmest part of the circumpolar deep water layer. And in some parts of East Antarctica, this water mass has actually warmed between 2 and 3 degrees, which is a massive increase in the temperature. And we linked this to the movement of parts of the Southern Ocean towards Antarctica. And in fact, in some locations, this core of warmest circumpolar deep water has moved over 200 kilometers closer to the continent. If we look at the time series of how this warming has been observed, I'm showing you the rate of warming in the 2 regions that I highlighted in the previous slides, and that is next to the Shackleton-Denman Glacier and within the Vincennes Bay where Vandervoort Glacier is. And you can see that circumpolar deep water has warmed an average of 0.72 degrees per decade since 1990, and this is double the rate of warming if we consider the whole time series since 1950. So it's really, since the 90s, we are starting to see a really rapid change in the water masses of the Southern Ocean that reach the continental margins of East Antarctica. So you look at the map, I'm taking you to Vincennes Bay. That's where the Vandervoort Glacier is. That's when one of the Australian Antarctic bases is, Casey Station. I'm gonna take you through a really busy slide here, but I want you to remember the slides that I showed before, where I showed a really well water column mixed with ocean temperature and salinity, pretty constant from the surface to the bottom of the ocean. And now I want you to look at the figure where I show the temperature and the salinity structure all the way between the surface to 2,000 meters. If you look at the blue lines, that's data that was collected in front of the Vandervoort glaciers in 1997. So these are summer measurements. So what we're seeing is warmer surface layers at the surface or near the surface, and that's the sea ice that's melted, the ocean is warming up during the summer months. But at the bottom of it, you can see the remnant layer of dense shelf water is still around the area. So you can see this really straight line that is telling us that this coastal polynya, it is actually very efficient in forming dense shelf water. In 2012, there was great success in putting a small CTD, small instruments in the head of seals, and they loved going to this area. So we have a fantastic coverage of temperature and salinity in the continental shelf, which is what I'm showing in the map on the right top corner of the slide. And there what we saw is that we didn't see dense shelf water dominating the bottom part of the water column. What we saw is circumpolar deep water dominating the bottom part of the water column. And the temperatures were as high as was observed in the near the Totten Glacier, which is one of the regions that is losing ice mass loss the fastest in this part of the Antarctic ice sheet. We've put some autonomous floats in the area, and that's what I'm showing on the top corner. Oceanographers like to put these complicated plots where we tend to lose everyone. So I hope you're still with me on this one. What I'm showing you in the top corner now is the relationship between the temperature and the salinity. And that's what we use to determine what type of water masses and how they were formed. So for dense shelf water, you see that it is there, and you look at the blue dots, it's really cold, really dense. And then you move to 2012, and that's where we have sealed data, and that shows a massive warming of over 1 degree in the water column between 500 meters and 1,000 meters. And then in 2022, where we got our next measurements from the region, we saw something in between. There was no dense water being formed in that polynya, but we didn't see that warm circumpolar water that we saw in 2012. But we saw a little bit of it. It was still there, and the water column had freshened significantly when compared to 1997. So we have an example of something in between. We have early measurements that show us a coastal polynya forming dense water, and there's some in the literature, there's some evidence that this region may have been able to form dense water that then form part of the Antarctic bottom water formation in the area. 2012, we see a picture that it is a lot more like West Antarctica, and then 2022, something in between. So this is a region that seems to be balancing between two states. I'm going to take you now to another region nearby that is also showing rapid grounding line retreat and ice mass loss. And this is in the Denman-Shackleton ice shelf system. The Denman Glacier is one of the glaciers discharging where the Aurora subglacial basin reaches the ocean. And this glacier is responsible for 1.5 meters of sea level rise equivalent. We dug into historical record of temperatures in this region, and we compare them to more modern records. So what I'm showing you here is that this region has seen a regime shift in that there has been a dramatic increase in circumpolar water and the dense water has been freshening. So we have something, again, in between West Antarctica with East Antarctica, at least for the polynya region. I'm showing you on the left part of my slide temperature and salinity at 2 different periods of time. In purple is all the measurements we had prior to 2010, and in the orange, all the measurements we have available after 2010. And you can see is that around 300-400 meters, we see a massive increase in temperature. And it's not just an increase in the temperature, it's a change in the water masses that form part of this polynya system. So we are seeing how things are starting to move and water masses are being replaced by others that we think they were not there before. Again, now in the right top corner, I'm showing you the temperature of the modified circumpolar water that has been observed with all the data that we collected. And you can see that there's been a rapid, because we have a big gap in between. But what is obvious from that figure is that the temperature of the circumpolar water is very different to what it was between 1960 and prior to the 80s, and that actually the temperature in all those years was pretty stable and constant, which is not the same as we see in the later part of the time series. We see in this, when you look at the structure of the water column, you tend to see something that is similar to what we normally call dense water, but it is a lot fresher than it was in the 60s, 70s, and the 80s. So we think that there is some relationship between the freshening in the polynyas. Then the polynya it has to work a lot harder to maintain the salinity of the water column in the area. And when you freshen it, that seems to be making the system more favorable for these warm waters to entrain in the continental shelf than before. I'm taking you back to the Southern Ocean because the system is tightly linked. In the previous slides, I said that denser water was really important for Antarctic bottom water formation. So this slide is showing you the link of what happens when denser water forms. It really dominates the water column at the end of the winter months and then spills over the continental slope and mixes with the warm circumpolar water, and then we see this really dense cold water mass occupying the bottom of the ocean around Antarctica. And this layer has been showing massive changes. And here I'm showing you a video from the results from Lee et al. Published last year in Nature, where they perturbed the system and they find out that the main result was that when you actually add meltwater forcing in the system, you are able to explain the warming signals we observed in the Antarctic bottom water. We also are able, or they were also able to explain why we see a reduction in the volume of Antarctic bottom water. And they, the model suggests that this warming and reduction in the flow, in the volume, is also translated in a reduction on the flow that affects the Southern Ocean overturning circulation. So this has an impact on the overall global overturning circulation. That controls how heat is recirculated around the globe. So we tend to worry a lot about the regions that are changing really fast, but I don't think I need to convince anyone here about the importance of long-term measurements. And if we didn't have some of those previous measurements in the past, and we went to these regions in East Antarctica, we probably thought that they were like that all the time, always have been like that. But what we are actually seeing is that this system is changing, and we don't really know what the feedbacks are going to move the system towards, and that's what we need to put a lot of emphasis for the future years. And I really liked this paper I'm showing here. It shows the strength of long-term measurements in helping and understanding how the system works and how it is changing. At the bottom, I'm showing you, at the bottom left, I'm showing you a time series of temperature and velocity from data underneath the Fimbul ice shelf. So if you look at the map, the red square shows you where the Fimbul ice shelf is. And they have been deploying temperature and salinity recorders and current meters and dissolved oxygen instruments under the ice shelf for since 2010. This is the longest time series that we have from under an ice shelf. And if you look at the map, this region is not particularly showing any alarm bells, but still, this time series has proven that the changes that we see in the atmospheric circulation and the ocean circulation around the Southern Ocean is starting to affect the regions where we are not seeing any change now. So it is actually helping us to understand how the system works, how things are interlinked, and helping us to help the models to put this process in place and making sure that when we do our projections, we have the necessary information we need to provide adaptation and mitigation advice. I'm reaching to the end of the slides, and I came to the presentation about the IPY, and I think the IPY is an inspiring program and an inspiring effort. So I dug into the data I had available in my computer last night and thought, let's see how much data was produced in the IPY, in the last IPY. So what I'm showing you here in these three plots is each black dot is a CTG station from a ship being made in the last 3 decades. And you can see how the sampling has moved around in time and space. The bottom, the middle figure shows the data that was collected from sheet-based observations between 2000 and 2009, and in red, the measurements that were taken in 2007 and 2008. So it is a really massive, it was a really massive effort, and we learned a lot from that. So we should use that as an inspiration for the next IPY. But you can also see that for the last decade, and I only had data up until 2018 available to make this figure. You can see that, you know, over time, we've learned the system is changing, and we all feel the pressure on learning more and more. And it is harder to get the logistics and the instruments that we need to understand the system. Fortunately, technology is advancing, and I want you to figure on the map of Antarctica and the Southern Ocean with the black dots. Each of those black dots represent temperature and salinity profile from the surface to 2,000 meters collected by Argo floats. And I show a photo of what an Argo float looks like. So these are instruments that has improved dramatically our knowledge of the Southern Ocean and how the Southern Ocean is changing for the last decade. But you can see in the white areas where we still have gaps, and those are the areas where the sea ice is, and these are the areas where critical processes happen, and they will determine how the system change. At the bottom, I showed the areas where seals that have been tagged with an instrument in the head have been collected information, and it's been great. They go to places where ships cannot go, and perhaps the one drawback was that in my wish list, you know, we still need the ship-based measurements because we get water samples, and that's where we measure the gas, and that's where we can learn about the carbon cycle and how, you know, a big gap is what this ocean circulation and this freshening in the Antarctic margins mean for the carbon cycle. And we have very few observations of that, so we do need those sheet-based measurements, while at the same time, we rely on the new technology to advance our knowledge. So I want to finish with this slide here. In 2007, there was a SUS Observing Under Ice report being written, and a few of us got together to describe what is it that we need to observe the Southern Ocean and the Antarctic marginal seas all the way to the ocean underneath the ice shelves. And we have made some advances in terms of the technology we use to measure the ocean and the ice-ocean interaction, but this is still a lot of effort needed. So my question for everyone here is, you know, what is going to be the role of the new technology in understanding ice-ocean atmosphere processes in the next IPY? We need both, and we cannot replace, you know, new technology with the old technology until the old technology is really completely replaced. So, yeah, big questions. At the same time, really exciting. Yeah, thank you.
Thanks for excellent presentation, Laura. We see the value of long-term monitoring and also how to move forward in a coordinated fashion. So we are all here to make that happen. So we're going to continue the discussion after this session. So let me invite Claire to take you to the Sea Ice Award. So, please.
Thanks very much. Yes, so I'm going to talk about sea ice at the interface of Antarctic boundary processes. Obviously, that's an enormous topic that we could do an entire conference series on. So my presentation is just going to be really about things that I'm actively thinking about at the moment, and I'm sure there'll be people in here that I don't cover an aspect that they are thinking of. So apologies for that. So I want to just start by talking about, how is sea ice changing and what have we been seeing in recent times about sea ice change. And then the latter part of my talk is going to be more about things that we're not really observing very well, and my ideas of priorities for what we should be measuring. So Antarctic sea ice anomalies, this has been in the news a lot. I'm sure everybody's highly aware that, we have a dynamic seasonal sea ice cover, very high variability throughout the satellite record on daily to decadal timescales. Up until about 2012, we had a very, very slight increasing trend in the sea ice cover. But the last decade or so, last 10 to 15 years, has been really quite dramatic. We've had absolutely high sea ice cover in the 2012, 2013, 2014, then a really dramatic drop, the size of which actually dwarfs the change in Arctic sea ice over the satellite record. And since then, we've had really low sea ice cover. We've had 3 out of the last 7 years, we've had very, very low summer sea ice. What's also very interesting about the recent change is just from the figures at the bottom here, you can see February is the winter sea ice cover, September, the summer sea ice cover, and it's pretty much low everywhere, all around. Earlier on in the sea ice record, we had regions, that very slow increasing trend I was talking about, kind of masked really big positive trends in some regions and very negative trends in other regions, and other places where it wasn't really changing very much. But now it seems to be that we have sea ice, low sea ice pretty much everywhere. Another really interesting thing is we have huge sea ice variability of the satellite record. That makes it very hard to really understand a trend. We've got just over 40 years now. But it seems that we have an increase in sea ice variability over the last 15 years. Will Hobbs did this really interesting study where he looked at some of the main climate modes like ICO, the zonal wave 3, the Amundsen sea low, and those are all the colored lines that you can see in the graph. So it's the temporal variability and the standard deviation of those climate modes. But the black line, where I've put those really big black arrows on, we've got a monotonic increase over the 21st century, but since 2014, we've got a real ramp up of the standard deviation. And it's pretty much doubled since 2006, the period just before 1979 to 2006 to the latter period. And it's significant at 99% level. Of course, that is very much swayed by the very, very low sea ice that we had in 2016. But Will Hobbs also took that data out and still found that there's a really large increase in standard deviation in recent years. So although we're getting very low sea ice, we're also getting very much more variable sea ice cover. Another interesting study that came out recently was this one by Ariane Purich and Edward Doddridge. And they looked at, again, it's very hard to statistically look at the satellite record. We have very, very few data points. But they found that, earlier on in the period, so where we had the blue bit in the top figure, where we've had this very maybe high sea ice anomaly period, then the spring maximum was related with the following summer minimum. But in this more recent period, their orange period, where we've got this very low sea ice cover, we're gaining sea ice memory, so the summer minimum is now related to the following spring maximum. So kind of indicating that perhaps things are changing in how the mixed layer depth is interacting with the sea ice. But of course, these are very short data sets that we're looking at to try and extract the statistical information from. It's also clear that, as I mentioned before, there's a shift to circumpolar patterns. So before we had much more variability. If you look at the Hofmöller plot on the right-hand side, if you look down between 1980 and 1990, we've got regions of red and mixed in with regions of blue around Antarctica. So there's places where we've got positive anomalies and places where we've got negative anomalies. But if we look in sort of 2019, 2020, we tend to just have red all around most of Antarctica. So it's happening everywhere now. There's something else at play. Going back to Will Hobbs' study again, so he ran a model. It was just a simple linear model where they used summer sea ice. They used some of the main climate modes together. It only uses the large-scale climate modes. The linear model sometimes truncates extremes. But by running this model, he was able to show that the climate modes alone don't explain the sea ice change. So we've always really understood before that the winds are really important and how the winds are affected by climate modes, and we'll hear more about that from Amelia later. But it seems now that there's a role perhaps of the ocean coming in that is becoming important. Going back to the Purich and Doddridge paper that came out early last year, we don't have a lot of data on the ocean, so this makes it very, very difficult for us to actually really understand how is the ocean affecting the sea ice. And the ocean is of vital importance to the sea ice. If the water doesn't get cold enough, then we don't get ice forming. But they were able to bring together Argo data, so from 2004, and really show that there does appear to be a clear warming in the data sets there. Again, this data is not comprehensive from around the whole of Antarctica. We need more data sets to really understand the role of the ocean. But it's clear that having this pattern all around the continent and it hints that ocean warming is now playing a role in how sea ice is developing. We need to understand better the role of the ocean. So there's been a lot in the press about Antarctic sea ice. We've had this very, very low sea ice recently. Not a lot is said about Antarctic fast ice. So fast ice is ice that doesn't move. It's called, I don't know why it's called fast, it doesn't move. So Antarctic fast ice is ice that doesn't move. It's linked to the bathymetry, so it tends to be within the 400-meter isobar. And it forms just because ice can get stuck in a region. So either because you've got an embayment, or it's behind grounded icebergs, or it's upstream of something that can hold the ice into place. In some places it's multi-year, so fast ice around Antarctica can be pretty old. And it's between 5 and 35% of the overall sea ice area. So obviously that's depending on the season of when it is. And the reason fast ice is really important is, if you want to find out more about land-fast sea ice, Alex Fraser has written an amazing review of sea ice, and of fast ice, I'd encourage you to look at that. What Alex has done recently is updated his record of fast ice, and I actually find this quite a scary plot. So on the left-hand side, you've got the anomalies in fast ice extent for 2024, and as you can see, it's pretty much red all the way around Antarctica. So we're losing fast ice everywhere, pretty much everywhere. And on the right is a time series showing fast ice extent, so it's a spatial average of fast ice extent. And you can just see that dramatic crash from 2023 to 2024. So although the story is that we're losing sea ice, we're having a dramatic fall in fast ice around the continent. I'm not talking about any of the ecosystem effects of sea ice change in my talk today, but I will just say that that's highly, highly important for habitats around the continent. There are many species that rely on ice, and especially fast ice, for breeding. And losing this ice is going to be quite horrific. My interest in fast ice is as a barrier, and as a protection, a buffer for ice shelves, and I'll talk a bit more about that in a minute. Another type of ice that's interesting that we perhaps don't know as much as we'd like to is platelet ice. So platelet ice is ice that forms due to supercooled water that comes up underneath ice shelves. And it contributes to sea ice mass balance, and it may indicate the extent of ice shelf basal melting. And so again, another type of ice that I think we need to focus on the different ice types as well as the broad picture of how sea ice is changing. So on to the impacts. I found the study really interesting that came out quite recently, which was looking at what is the effect of changing sea ice cover on the radiative effect. So how is sea ice changing the albedo? And through most of our satellite record, there hasn't been a huge planetary cooling effect of changes of Antarctic sea ice. But you can see the dramatic change since 2016 of the change in radiative effect. So the 7 weakest years of Antarctic sea ice radiative effect all occurred since 2016. And that change means we've got 12% less cooling for Antarctic, due to Antarctic sea ice over that period, compared to 20% for the Arctic. And this disappearing sea ice globally, so this is a global number, means that the Earth's absorbing an additional 0.3 watts per meter squared of solar power for each degree Celsius of global warming. And if we're reducing the sea ice cover every year, that's quite significant. So this is where I mentioned fast ice as a really important component of really understanding ice shelf stability. There was a really interesting study by Massam et al. 2018, and they really showed that ice shelf disintegration has been a really big part of some of the really big, so removal of fast ice has been a really big component of ice shelf disintegration, especially for the Larsen A and B and Wilkins ice shelves. We don't yet have a proper parameterization that accounts for sea ice and swell. And so we really need to understand where do we have sea ice and how does moving that fast ice then affect how wave energy is transforming onto the shelf, and how is that going to then affect carving. This is mostly swell that we're talking about, so very long period waves are very largely unaffected by sea ice, obviously very important for the ice shelf. But where I'm talking about interest in sea ice, we're looking at like swell waves. Another study by a different Fraser this time, 2022, has also shown how sea ice processes really control ice shelf instability. So they showed that the increase in sea ice in the wet LC over 2003 to 2019 actually explained advance of the eastern Antarctic Peninsula. But if you remove that sea ice, then of course, then you lose some of that back pressure that you get from the pack and the fast ice, and you then don't get ocean waves attenuating. So I'm quite interested in waves and sea ice, and I'd really like to understand how is it that great storms, we know there's enormous storms in the Southern Ocean, how do they then move through pack ice, move through fast ice, and then onto the shelf, and then what is the repercussions of onto the shelf? I'm only aware of 2 existing studies that have measured, using seismics, have measured actually wave transformation onto the ice shelf. However, a growing number of studies are really highlighting how important this is. When you have carving at the front of the ice shelf, you get breakup of huge pieces of icebergs, also mixing in with the sea ice, the waves in ice melange. We don't have any studies on that. We don't know how waves are transforming through that portion of the ocean. This is a tricky one to address. Where do you put your buoy measurement if you've just got completely heterogeneous mix of ice melange? Waves in fast ice, we're starting to understand a little bit more about that. We don't really know how much fast ice blocks waves, and this is the process by which fast ice does protect the ice shelf, is through this wave blocking. We think it's probably greatest for shortest waves, but we need more observations to understand this. And we think that thicker ice blocks more than thinner ice, but again, we don't really have the observations to know this for sure. We know a lot more about waves in sea ice, so there have been numerous studies so far, but not yet studies that examine different ice types, and we don't know very little about what's the difference in attenuation for big versus very small flows of ice. So ideally, we need more experiments that will observe changes in wave height, direction, and frequency for ice of varying thickness, but also varying types, if we are really to hope to understand how we transform onto the ice shelf. My next few slides are just highlighting some of the things that I think we don't understand very well yet, and that we really need observations to help us to understand. So there's a couple of wave feedback processes that intuitively make sense, but have not really been that well examined or that well understood, or data available to really understand it. So one is positive summer feedback. So that's where during the warm period, you've got waves approaching, they weaken the ice cover, and then that breaks up the ice cover, then for the waves can propagate further into the ice. There's only been a few studies on this, and I think we really need to try and understand how the positive feedback process works. We know that waves keep sea ice unconsolidated, but we don't yet know we don't really understand fully how this feedback process works. Even less well understood is the negative winter feedback. So this time you've got increased wave activity, and then because it breaks up the ice, it opens up an area that then freezes more quickly because it's cold. So we produce more ice growth, a bit like a polynya, so it's a bit more like an ice factory here, which then should reduce wave activity and allow the ice cover to strengthen. But we don't have any observations that actually can demonstrate that this is the case. So this is another feedback process that I think is really important for us to analyze and understand, so that if it is indeed important, it's included in the models that we have. And then, yes, just some processes that I think that are really poorly observed and poorly understood that really we should be focusing on. So in terms of wave-ice interactions, we don't really understand properly wave dispersion and attenuation in sea ice. And we need to measure these at the same time as understanding the sea ice properties. So existing observations, we don't always know how we can measure how the ice is changing. So if you leave your buoy on the sea ice, and then you go away and you're getting the data back by iridium, you don't have a picture of what the ice looks like. So maybe the ice is breaking up, maybe you just don't know. So we really need to understand the sea ice properties that are changing along with the waves that you're measuring. We know that wave radiation stresses are likely to play a role in dynamic instabilities and thickening, but again, we don't really have any observations that can help us to identify how important this is and put it into the models. Ice mass and momentum balance transfer. So obviously the ice is at the interface of the atmosphere and the ocean. We want to understand how wave energy can drive upper ocean turbulence, and getting observations of this is very challenging in Antarctica. Any that we do get are maybe during the summer. So all-round observations of upper ocean turbulence, I think, are really, really important. And then in terms of rheology, so we don't really know about how we change from different ice types. So how do we change from consolidated ice to broken up flows? How do these changes in ice strength and viscosity depend on the flow size, on the porosity, on how much fragile ice we have, what the wave condition is? We don't know right now. So just some concluding remarks. Antarctic sea ice has recently been characterized by record minima. We don't know if that's a temporary thing, and maybe we will have record maxima again next year. Antarctic sea ice always seems to surprise us. The last decade has shown increasing variability. I'd like to highlight again how low the fast ice is around Antarctica this year, which I think is a really big warning sign for us all. Ocean warming is likely to be playing an increasingly important role. As I said, we don't really know how sea ice is evolving at the moment through time, but it's obvious that with a warming ocean, eventually, if it gets too warm, you won't be able to form ice. There's building evidence that maybe we are encountering a critical transition in Antarctic sea ice, and this has obviously implications for ecosystems, which I haven't really touched on at all, global climate and how it changes albedo, and also sea levels. So the ice in front of the ice shelves is really important for ice shelf stability. We don't know what drives extreme states of sea ice, so we're still trying to identify what it is that is causing Antarctic sea ice to be so low right now. And then we don't really know how things respond to these extreme states. So we need more causal analyses to isolate specific drivers. So perhaps a sort of work like François Massenet did in 2012 to look at very high Antarctic sea ice cover. And much of our lack of understanding is due to a lack of data. Thanks very much.
Yeah, thanks, Claire. Actually, to me, I've been really frustrated with the sea ice whenever we get down there to the ice. So hopefully we're going to have a really good idea of how the sea ice behaves in the future. Thanks. And then let me invite Emilia, the last talk. So please.
Hi. Continuing this symposium, I'd like to talking about ice-ocean atmosphere interaction and teleconnection accelerating Antarctic mountain year. And this diagram showing the very simple idea about what is the ice-ocean atmospheric interaction and teleconnections, especially for Thwaites Glacier melting in West Antarctica. Of course, there are a lot of more processes related with those Antarctic melting, but I just want to show you the very simplified version of the interactions. And tropical forcing or extratropical forcing can change the local circulation in Antarctica and ocean current via teleconnections. And then it can in turn to change sea ice and ocean temperature and salinity under the ice shelf, and also can making some kind of anomalous snowfall. On the other hand, the meltwater discharge from Antarctica can alter the sea ice and then ocean current and local circulation surrounding the Antarctica, and then it can also having a big impact on the global climate. And thinking about this type of interaction in the left panels, and there have been a lot of study. So now we have a lot of the interactions and teleconnection related with the ENSO and AMO, MJO, and IPO, with the local circulation such as SAM or ASL. And then thinking about the meltwater discharge from Antarctica, and those kind of studies mostly using the model. And then the modeling static of Antarctic meltwater really show us that the Antarctic meltwater play a role in delaying the global warming. However, the uncertainty in model really limiting our understanding about those issues. So there are a lot of efforts is underway to reduce the uncertainties related to the Antarctic meltwater right now. And then I'd like to introduce some research outcome from our group related with those interactions and teleconnections under the project K now, actually. And then this map showing the El Nino and then the change in ice mass over West Antarctica. And we all know the West Antarctica really suffering from the ice loss a lot, but what we found out, there are kind of the delay of the mass change in 2016, and which is related with the very strong El Nino happened in the 2016s. So what we found out is the occurrence of very extreme precipitation can be happen in West Antarctica related with the very strong El Nino, and then processes the right panel, if you can see that. So in Australia autumn, the wave response to the ENSO becomes stronger and reach in high latitude owing to the appearance of the subtropical jet, which form a double jet structure with the polar jet. So it can really, bring a lot of moisture from the extratropics to the inland. So it can causing a lot of snowfall, and then snowfall can really compensate the Antarctic melting. So if we just see the overall trend, the melting, the losing the Antarctic mass is slightly stopped for those years. However, so what you know is the El Nino significantly impact the West Antarctica's climate, driving atmospheric and oceanic change that alter the ice mass. But the global warming can really alter those relationships. So if you see the left upper panel, actually the more warmer climate can changing the position of the El Nino forcing, and also it can changing the jet expansion, and it can also changing the wavelengths of the teleconnections. So those whole impact can really causing a very different outcome for the future climate. So this is the one example what you found out. So as I said, that the occurrence of extreme precipitation is linked to the strong El Nino event. However, the relationship between El Nino and West Antarctic precipitation vanished in the higher emission scenario like that way, because the other factor having a very linear relationship with the warming climate. But if you focusing on to the right top panel, actually the center of action of the emergency row position is not really having a linear relationship with the global warming forcings. It does have a tipping point of 1.6 degree. So that really, we can interpret those results like that way. If carbon neutrality is achieved and then global warming is kept below 1.6 until 2100, this resilience is expected to continue with increased El Nino-induced snowfall, which can help compensate for ice mass loss. But we are gonna having the more stronger warming than 1.6 degree, and those compensating effect will be disappear, so the ice mass melting gonna accelerating. And then this result is for the East Antarctica. And we know not only West Antarctica, East Antarctica also suffering from the ice mass loss. Of course, the amount is smaller than the West Antarctica. So we try to find out the outer forcing from the local processes here. So if you see the left top panel, this is the reduction of the ice mass, and then you can find out the red area, which having the very strong loss signal here. And then we analyzing the relationship between those East Antarctica mass with those important indices, such as IOD or Nino index and AMO and SAM. And what we found out is actually the Indian Ocean dipole is primary factor reducing the East Antarctica precipitation, while the other modes such as SAM has only localized impact. And ANSO and AMO has a very minor impact for those variability. But more interesting feature is that this IOD precipitation correlation have fluctuated such as like decadal variability. So with recent resurgence linked to the SSC anomaly in the Southern Indian Ocean. So Southern Indian Ocean warming really causing the more stronger relationship between IOD and precipitation over East Antarctica for recent years. And then we also try to understanding the variability of sea ice related with those teleconnection context. So this study examined how ANSO and IOD influenced the West Antarctic sea ice during Australian spring. And then what we found out is ANSO and IOD together account for 20 to 30% of sea ice variance driven by dynamic and thermodynamic mechanism linked to the atmospheric circulation in Amazon, Bellinghausen Sea area. And then by conducting the more model experiment for ANSO and IOD separately, what we found out is that ANSO's impact on ABS region is about 3 times stronger than that of IOD. So what you can say is ANSO is the major player for those internal variability. And now move to the impact of meltwater from the Antarctica. And this recent study published in the Environmental Research Letters, this is the outcome from the model experiment. And then what we found out is this is the impact from the Antarctic meltwater globally. And what we found out is future increase in Antarctic freshwater discharge could cause regional cooling, which atmospheric and oceanic dynamics might spread globally, and lowering global temperature and strengthening Atlantic Ocean circulation, which is well matched with the previous result. But one interesting thing we found out is this mitigating effect is time dependent. There is a fast and slow responses of Atlantic meridional overturning circulation to Antarctic meltwater forcing. So if you see the left upper panel, the red arrow, while global temperature consistency decrease, Atlantic Ocean circulation initially slowed down in response to the Antarctic meltwater due to fast atmospheric teleconnections. But after that, the whole globe is cooled down, the amount is getting stronger again. So it's having the kind of different non-monotonic response from the meltwater force. And this result showing, actually I should say, like this is the first research talking about the impact of Antarctic meltwater on East Asia. And this result showed that the Antarctic meltwater can cool down the whole globe, but for East Asia, it have a localized warming impact to intensify the global warming throughout the teleconnections. And this is related with the change in tropical forcings And so even though the whole globe are cooled down due to the Antarctic melting, actually East Asia having more additional warming due to the teleconnected effect like that way. So those research can be concluded like that way. What you learn from those previous study is atmosphere, ice, ocean interaction, and teleconnections really have been studied across various spatial and temporal scale with general variabilities. And then the mechanism affecting Antarctic ice sheet and mass and the sea ice variability is kind of our main interest. And then El Nino can increase snowfall in West Antarctica, but intensification of warming make it vanish. And then the mass loss in East Antarctica is related with the Indian Ocean dipole. And then the variability of sea ice in the Amundsen Bellinghausen area is related with the ANSO. And then Antarctic meltwater can make the AMOC slow down at first, and eventually it can make it stronger again. And then the Antarctic meltwater could potentially intensify the warming in East Asia. And then, actually for recently, rather than that, there is kind of the emerging issue for our research area. And actually it is related with our base, which is located into the Low Sea, the Jangbogo Station. The recent sudden decrease in Antarctic sea ice caused the complete melting of ice in front of the Jangbogo Station for the first time in 10 years, severely disrupting our research activity in front of those areas. I just showing the very simple video here, and you can find out, the sea ice in front of the Jangbogo Station is totally disappearing with the more larger footage of the ice loss in front of Jangbogo Station here. If you see in detail, actually it just disappeared just less than 6 hours. So we never really see those phenomena, and we never predict. So in this context, what we found out is there are kind of the area we should research more in terms of interactions and teleconnections. So under these circumstances, we're developing the new project following to the KNOW. Actually, KNOW have a goal to project the sea level change due to Antarctic melting. So for that, we have studied about melting and breaking up, mass balance, and feedback and projection. So we try to understand the full mechanism and interaction related with the sea level rise. While the new project, so-called FAST, is designed to produce seasonal Antarctic sea ice prediction, so we can supporting our Antarctic expeditions and actually infrastructures. So this project have a component of the Antarctic sea ice observations, and then we, based on the observation, we're gonna developing a sea ice model. And then we also creating a state-of-the-art ice model and AI-based seasonal prediction data systems. And we also plan to establishing an international cooperation network for Antarctic sea ice prediction modeling, and then try to participating the international activities such as Spin South. And then also global factors influencing the Antarctic sea ice change and their global impact will be investigated under those new projects. And this project is already endorsed by WMO, WWRP, PCAPS, and then 12 institutions from 8 countries is to cooperate. So actually, this project is the initiate from the one international workshop. International workshop on sea ice prediction model was held in last October. And then for those workshops, actually the 40 scientists and young students discussing about the recent sea ice decrease issues and talking about how we can predict and model those phenomena here. So out of those workshops, we published the workshop report in BAMS, and based on those discussions, I building this new project at FAST. So FAST structure looks like that way, and then whole process of FAST is having some component of the international collaboration, like that way. And then final goal of the FAST will be producing the high resolution sea ice seasonal prediction, especially in the region of the Ross Sea. And then in this context, we are very interested into the characteristics of circumantarctic fast ice variability, because the lot of sea ice research from the previous talk from Claire actually focusing onto the expansion of sea ice to the Southern Ocean or international variability of the sea ice related with the other global climate variabilities. But we are very interested into the fast ice just in front of the ice shelf. So this is the one example we are researching about those issues. So fast ice contribute to the mechanical stability of ice shelf and influence coastal polynya size, ice production, and dense water formation. So this research explored the link between large-scale atmospheric pattern and circumantarctic fast ice variability, highlighting how non-zonal SAM characteristics in the weather and Amazon Sea affect sea ice and fast ice, particularly in the DML and AS region. So what they found out, the fast ice did have internal variability related with the SAM, but not whole area. Only just two regions was come up. The one is the Amazon Sea region, and the other one is DML region. And then there are some processes related with the SAM, and then the large-scale sea ice, and then surface wind, the ocean swell, and short-wave flux having kind of the feedback processes, and eventually it really decaying the amount of fast ice in those regions. So it will be kind of the first step to start to about the understanding of sea ice and fast ice interactions. So I'd like to give my conclusion remark in here. The Antarctic ice sheet, ice shelf, and sea ice are still among the most uncertain elements of the global climate system, highlighting the need for improved modeling to better understand and predict their behavior. So the comprehensive research on interaction teleconnection mechanism conducted across these two projects, KNOW and FAST, led by COPRI, is expecting to provide crucial insight for understanding and predicting the complex change occurring in Antarctica. And additionally, through active participation in and promotion of various international cooperation programs, this research aims to generate synergetic outcome by strengthening the global collaborations. And furthermore, this effort will help pinpoint and define additional area needing the collaboration, guiding future joint initiative. That's it. Thank you.
Thank you, Emilia, for the excellent talk. We had a really long journey from the continents, coastal regions, and ice-ocean interaction, and then finally the interactions between the crosshairs and the rest of the world. So the thing is that we did not spend carbon emission through that journey, so which is great. So given that the time constraint, probably we may have a couple of quick questions from the floor. So, anyone? So I knew that. So usually I'm an Antarctic scientist, so all the time I have a contingency plan. So I have a couple of questions for them. So actually, I observed that through a couple of days from the Sunday, and then the thing is that most of us are really wanting to have more data. So the thing is that even though we have really coordinated efforts to make that happen, but I believe cutting-edge technology or the emerging technologies help us a lot for being kind of sustainable and then long-term observation monitoring system. So I have one question for Kenny and Laura, which is, what role can emerging technologies such as airborne survey, autonomous underwater vehicles, even the animal taggings, and remote sensing play in improving our understanding of the Antarctic melting frontier? So, Kenny?
Sorry, it works. Yeah, it's quite a long question.
Oh yeah. So
I try to answer as short as possible. I think that yeah, combination is really important, and then probably in the airborne geophysics, drone is most important. And then but then really combination of the conventional tools and the new tools are key solution in my view.
Yeah, that's a great question. And I think in my wish list, we want to put instruments and go on the ship everywhere. And I think that that's going to be a challenge for East Antarctica. A lot of what we know of what's happening in West Antarctica is because there's been a great international effort and collaboration in working in the Amundsen Sea. But we've seen that there's so many regions in East Antarctica that are changing, and they are challenging on its own way. So we'll have to think carefully how we address that. And more doesn't mean better. So I think that having some targeted process studies that tell us what are the essential processes that we need to monitor may be the key to implement a long-term sustainable monitoring program.
Great, thanks. Any questions or comments from the floor? Okay, I cannot see anyone who's raising hands. Probably it's like kind of coffee break, so everyone wants to out for a coffee. So thanks again for our excellent and distinguished speakers again. And then this is not a this is just a really good start for like exchanging our ideas, and then hope to continue like a really productive discussions over the rest of the conference. Thank you again. Muchas gracias.